I'm Reimi Guerzon, and I'm here to discuss the introduction about a research article, Recent Progress on Piezoelectric and Triboelectric Energy Harvester in Biomedical System. For introduction, implantable medical devices. These devices is one that is placed inside your body during a medical procedure such as surgery and is intended to stay there after the procedure. These implants are made from skin, bone, or other body tissues. Others are made from metal, plastics, or ceramic. Examples of IMD. First is sensor. Implantable sensors have been used in medical research for measuring parameters such as force, torque, pressure, and temperature inside the body. Although sensors and electronics have been built into orthopedic implants, they tend to be bulky, costly, and unreliable. Second is pacemaker. A pacemaker is a small device that is placed in the chest or abdomen to help control abnormal heart rhythm. These devices use electrical pulses to prompt the heart to beat at a normal rate. So how does it work? A pacemaker consists of a battery, a computerized generator, and wires with a sensor at their tips. The battery powers the generator at both are surrounded by a thin metal box. The wire connects the generator to the heart. If the heart rhythm is abnormal, the computer will direct the generator to send electrical pulses to the heart. The pulses travel through the wires to reach your heart. Newer pacemaker can monitor your blood temperature, breathing, and other factors. They can also adjust your heart rate to change in your activity. The third is implantable cardioverter defibrillator. An ICD is a battery-powered device placed under the skin that keeps track of your heart rate. So, how does it work? If your ICD has pacemaker feature, when your heartbeat is too slow, it works as a pacemaker and sends tiny electric signal to your heart. When your heartbeat is too fast or chaotic, it gives defibrillator shocks to stop the abnormal rhythm. Fourth is cochlear implants. A cochlear implant is an electronic device that restores hearing to profoundly hearing impaired adults and children. Its components can be bifurcated into the external and external parts. The internal components, the receiver stimulator, and the electrodes are surgically placed inside the ear, and the electrode is placed within the cochlea, respectively. The external components are worn much like a hearing aid and consist of microphones, processor, and transmitter. Now that we are done with the examples of IMD, we now proceed to the mechanical energy. Mechanical energy considered as one of the most popular and sufficient power in a living creature. By harvesting in vitro and in vivo biomechanical energy, self-powered medical electronics such as IMD for nearly lifetime can be attained. In this mechanical energy conversion process, many techniques such as piezoelectric effect, triboelectric effect, magnetostrictive effect, and electromagnetic induction can be. Energy harvester. Extremely flexible and lightweight energy harvesters are settled conformally on muscles and organ surfaces. These devices are fabricated on plastic thin films such as PET, PI, and PDMS. It is widely used in flexible electronics because of their appropriate flexibility and strength. Also, they are biocompatible, meaning they cannot cause harmful effect inside the. Let's now proceed to nanogenerator. Nanogenerator are energy harvesting devices. So the first nanogenerator is PENG, which is piezoelectric nanogenerator. This device capable of converting external kinetic energy into electrical energy via action by a nanostructured piezoelectric material. Piezoelectric nanogenerator can be categorized into two types, Ling and Bing. So Bing, vertical nanowire integrated nanogenerator. It has three parts, base electrode, vertical piezoelectric nanostructures, and counter electrode. Nanowires grown from the base electrode to the counter electrode. It has a 3D configuration. Ling, which is lateral nanowire integrated nanogenerator, integrated on a flexible substrate An individual NW is subjected to high tensile strain and allows for amplification by series connection of units. It has 2D configuration. So what are the applications of this nano generator? Self-powered nano micro devices, smart wearable system, transparent and flexible devices, and implantable telemetric energy. We now proceed to the second nano generator, which is triboelectric nano generator. This device can convert the external ambient mechanical energy into electricity based on the nanoscale triboelectric effect. It is another mechanical energy harvesting technology besides the piezoelectric. So what are the materials used usually in triboelectric nanogenerator? Almost all materials. Gaining or losing electrons depends on the material polarity. Surface morphology is more important, and composite material. So the major application of Tang, it is a suitable power source or self-powered sensor. And the Tang, with rationally designed structure, can convert irregular and mostly low frequency mechanical energies from the environment, such as human motion, mechanical vibration, moving automobiles, wind, raindrops, and ocean waves.
My name is Paula Aquino, and I'm here to discuss the energy conversion mechanism. So here's an overview of the energy conversion mechanism topics. So first is we're gonna talk about the piezoelectricity, and second is the triboelectricity and electrostatic induction. And under this is the vertical contact separation mode, the lateral sliding mode, the single electrode mode, and the freestanding triboelectric layer mode. So let's talk about piezoelectricity. So applying PENGs to harvest mechanical energy has received a great amount of attention due to its diversity of sophisticated design for direct conversion of mechanical energy into electric power for various integrated applications. The nature of the piezoelectric effect is closely related to the generation of electric dipole moments in solids. The dipole moments may either be induced by ions on crystal lattice sites with asymmetric charged surroundings or may be carried by molecular groups directly. So in figure 2a, let's take the zinc oxide crystal of first site structured as an example. So the tetrahedrally coordinated zinc and oxide are accumulated layer by layer along the z-axis. At its original state, the charge center of the anions, the cations, coincide with each another. Once an applied external force was applied, the structure will be deformed. It could be either stretching or compressing. In figure 2b, it shows the negative and the positive charge centers that are separated and can form an electric dipole leading to a piezoelectric potential. If an external load is connected to the deformed material, the free electrons are driven to partially screen the piezoelectric potential and flow through the external circuit to realize a new equilibrium state. So in figure 2c and figure 2d, a current pulse flowing through the external circuit is continuously generated when the piezoelectric potential is altered sequentially by applying a dynamic external force. This primary mechanism of piezoelectric potential generation applies to various piezoelectric materials. So PENGs mainly consist of piezoelectric materials and flexible substrates. Two core factors for developing PENG are material choosing and device structural design. So another energy conversion mechanism is the triboelectricity and the electrostatic induction. So the triboelectric effect, which has been known for thousands of years, is the electrically charging process when two different materials contact each other through friction. Despite this is one of the most common phenomena that is seen every day, the mechanism of the triboelectrification is not very clear yet. So the process of chemical bonds formed between some parts of the surface in two different contacted materials and charges moving around from one material to another due to different stability to gain electricity is generally believed. The charge transferred between two materials can be molecules, ions, and electrons. When two materials are then separated, some of these bonded atoms tend to maintain the additional transferred electrons, and some tend to give them away, which possibly give rise to the opposite charges on different friction materials. The opposite charges on both friction surfaces can generate a triboelectric potential, which can drive electrons in the back electrode to flow in order to balance the created electric potential drop. So, on the basis of the principles that I mentioned in the previous slide, there are four kinds of things with different modes that have been invented, which can be seen in this figure 3. So these are the vertical contact separation mode, the lateral sliding mode, the freestanding triboelectric mode, and the single electrode mode. So for the vertical contact separation mode, so the first design of thing is shown in figure 3a. So these are the example of the vertical contact separation mode. So two different dielectric films place as top and bottom friction layer, and electrodes are deposited on outer surfaces of the friction film. So the opposite charge is created between the surfaces of two conducted dielectric films. When the external force is released, the two dielectric films are separated with each other, accompanying with the electric potential drop between the friction surfaces. So after connecting the two electrodes with a load circuit, free electrons would flow from an electrode to another, driven by the electrostatic field. Once the gap becomes closed, the electric potential created by the triboelectric effect will disappear, and the electrons will flow backward. So another kind of tank is the lateral sliding mode. So in here, the original structure of lateral sliding mode and the vertical contact separation mode had the same starting position. So in this figure, a relative parallel sliding creates a triboelectric charges on both surfaces when two friction surfaces contact. So these electrons then will have two electrons that are driven to flow by the triboelectric charges, which is generated by a lateral polarization introduced along the sliding direction. So with the periodic process of sliding apart and closing, this lateral sliding mode then generates an AC output. So the sliding can be a planar motion, a disc rotation, or a cylindrical rotation. Related studies of mechanism have been used to improve the basic mode and grating structured tank. So another kind of tank is the single electrode mode. So these two kinds of modes that were mentioned previously contains two friction layers and two electrodes that are interconnected by an external circuit. So such tanks can work independently and be freely moved, while in some other cases, a mobile object can be one electrode of the tank, which do not need to be electrically connected to the load, such as a human jogging underground. For scavenging mechanical energy in these cases, single electrode tank is created. The bottom electrode is grounded in single electrode mode tank, which can be seen in this figure. So the local electrical field distribution will be changed with the top object approaching or departing from the bottom film, resulting in electron flow between the ground and the bottom electrode to match the potential change. In both contact sliding mode and contact separation mode, this energy harvesting strategy has been applied. So the last kind of tank that we are going to talk about is the freestanding triboelectric layered mode. So in this figure, we can say that a moving object such as our clothes, gloves, and shoes is usually charged by contacting with air or ground. So the electric charges can maintain on the surface for hours. Due to the density of electric charges achieves a maximum, there is no necessary to do friction or contact during this time. So a pair of symmetric electrodes is designed under a dielectric film, and the width of the electrodes and the gaps are of the same order with the moving object. With the object approaching to and departure of the electrodes, an asymmetric electric charge distribution on the surface of materials can be created, which causes the electrons flowing from one electrode to another to screen the potential distribution. So between the paired electrodes, an AC output is generated by the oscillation of these electrons. Because there is no direct friction or touching between the moving object and the top dielectric layer of the electrodes, an abrasion of the dielectric layer can be completely reduced. This approach will greatly enhance the durability and prolong the service life of tanks in rotation mode. So the harvesting energy from human walking, automobile, and other moving objects is feasible and convenient.
And now for the methods and methodology part of the article, we will discuss about nanowire devices, thin film devices, and triboelectric devices. So this review article focused on nanowire devices, and the name piezoelectric nanogenerators or PENGs was defined by Wang's group in 2006 when they found piezoelectricity in zinc oxide nanowire. So in this section, the author briefly reviewed the working mechanism, modeling simulations, and the experimental progress of piezoelectric nanogenerators according to the structure of the nanogenerators, including the vertical aligned nanowire arrays, the lateral aligned nanowire networks, and some other similar structures such as nanobelts and nanoribbons. On this part of the review article, we will discuss about the lateral nanowires. So PENGs built with single zinc oxide nanowire or lateral nanowire arrays have been well established, providing various delicate nanoscale devices for multiple applications as seen on this figure. In a typical case, both ends of a single zinc oxide nanowire was fixed by silver paste as electrodes. The zinc oxide nanowire and two electrodes were packaged on a flexible substrate laterally. A uniaxial tensile strain was induced by the bending of the substrate that causes a piezoelectric potential along the zinc oxide nanowire, which drove the electrons to flow between the external circuit. A pulse current signal was generated by zinc oxide nanowire-based PENG in a repeated bending releasing process, as seen on Figure 8. However, the output performance of PENG based on single zinc oxide nanowire was relatively low. The open circuit voltage or VOC was about 20 to 50 millivolts, and short circuit current was about 400 to 750 picoampere, which limited their applications of energy harvesting as seen on Figure B. So for enhancing the output of zinc oxide-based PENG, a direct approach was to integrate numerous lateral zinc oxide nanowires in a single device. As shown in Figure C, nearly 700 rows of zinc oxide nanowires were integrated on a single flexible substrate in a parallel configuration. Each row in this configuration contained about 20,000 zinc oxide nanowires. This made the whole device exhibit great flexibility. So the lateral zinc oxide nanowire array was utilized in a sweeping printing method to fabricate high output PENG, and this was reported by Zhu and his group. Next, we have the vertical nanowires. So similar to the above-mentioned lateral nanowire devices, the vertically grown zinc oxide nanowire arrays that have consisted polar directions can also be used to convert mechanical energy into electric power, as seen in this figure. One of the most acceptable methods to fabricated vertical zinc oxide nanowires is solution-based wet chemistry method, as seen in Figure C. The working principle of this kind of PENGs was just similar with that of the former mentioned PENGs based on the lateral zinc oxide nanowires. The piezoelectric potential generated electron flow, which was controlled by the Schottky barrier between the interface of metal electrode and the zinc oxide nanowires, as we can see on figure B. However, when built into a flexible device, the electrodes in this kind of energy harvester may appear some problems of mechanical durability, which makes it against the lifetime and the stability of the device. Therefore, in the manuscript, they provided a potential solution by using single-walled carbon nanotube or CNT networks as conductive electrodes. Due to its improved contact between the nanowires and electrodes, the output of this PENG was significantly enhanced, and meanwhile its durability and stability was exceptional compared with former devices. The same group further developed a flexible and transparent PENG consisting vertically grown zinc oxide nanowires using the conventional solution growth method and 2D graphene electrode. The 2D graphene electrode has exhibited extraordinary electrical and mechanical properties in comparison with other electrode materials, which made it an attractive candidate in the application of flexible electronics. By coupling of the piezoelectric effect and the electrostatic induction, electron flows went back and forth in the external load induced by an iterative mechanical deformation applied on the device. The output voltage and the corresponding current were up to 20 volts and 8 microampere, respectively. However, this high output PENG typically was 1 to 3 millimeters in thickness, which will normally result in the large percentage of consumption of the mechanical energy that was input. Therefore, this PENG was not conducive for small-scale mechanical energy conversion when applied in biomedical systems. In consideration of this drawback, Lee and his group developed a super-flexible PENG with the same principle by using an aluminum foil as both the substrate and the electrode, as we can see in figure D. Next, we have thin film devices, which is PZT-based PENGs. So PZT, or lead zirconate titanate, is a traditional piezoelectric material that is preferred by researchers for its higher electromechanical coupling coefficients than many other conventional piezoelectric materials such as barium titanate. So for a long time, due to its fragile nature, PZT thin film was considered inflexible and not stretchable. A structural failure will be caused by a stretch and slide scale, and a 0.2% is the maximum safe strain range of PZT. Researchers have proposed various innovative designs of PENGs based on the different morphology and characteristics of PZT to overcome this undesirable property. So in this section, Park and his group reported a large area and highly efficient PENG with PZT thin film on flexible substrates. An inorganic-based laser lift-off or ILLO process was used in this method. The size limitation of PZT thin film was eliminated by the ILLO process, resulting in an output increase of the flexible PENG as seen on figure A. Moreover, a bio-inspired flexible PENG based on the barium titanate was presented in 2013 as seen on the right panel. In this work, anisotropic barium titanate nanocrystals were deposited on a viral template via the metal ion precursors self-assembling. The filamentous virus provided template for the deposition of an anisotropic entangled highly crystalline barium titanate nanostructures. This flexible nanogenerator based on virus-enabled piezoelectric structure can generate electricity of about 6 volts and 300 nanoamperes without additional structural stabilizers, indicating the high output related to the important structure in nanoscale. So this method of using biotemplate is facile and with particularly enlightening meanings for flexible PENG designing and applications. Moving forward to triboelectric devices, device structure design is the key highlight of this part. So the material properties including friction, work function, electron affinity, and so on play important roles in PENG's output performance. Basically, nearly all materials can exhibit triboelectricity, so pairing the right materials can achieve output in maximum. Since the first demonstration of TENG, the arch-shaped structure has become one of the most popular structures due to its simple fabrication, high performance, and universal feasibility. In this structure, TENG with an arch-shaped gap between a polymer film and a metal foil was fabricated as seen on Figure A. So the energy conversion efficiency reached up to 39%. Inspired by this structure and its working mechanism, various derived structures are proposed. For example, arc-shaped and anti-arc-shaped TENGs were consistent to alternatively stacked structure and electrically connected in a parallel configuration, which has been proved that can significantly enhance the output performance, as seen on Figure B. So the zigzag structure was another variation of the stacked arc-shaped structure on Figure C. So considering the rapid development of deformable and stretchable electronics, a power source, structural and functional, suitable for this class of electronics was needed. Yi and his group reported a method of TENGs and highly deformable and stretchable self-powered sensors. A shape-adaptive triboelectric nanogenerator unit with conductive liquid as electrodes can be used to harvest various mechanical energy effectively in different motions as seen on Figure D. So because of the fully soft structure, this system can subject to large degree deformation and convert energy from various motion, including human body movement, as we can see on Figure E. This self-charging power system shows wide applications to harvest all kinds of biomechanical energy.
This section discusses about the recent progress in biomedical applications. The recent development of biomedical systems, especially the microelectronic devices for healthcare and other medical applications, illustrates the potential of such futuristic concept. Some possible applications are exciting and extensive, but they still need reliable and safe energy sources to operate. Considering the application in biology and medicine, batteries can be dangerous, bulky, and difficult to operate. In human body, where there is little light and there are only small thermal gradients, mechanical energy harvesting is an ideal method to provide power for implantable medical devices. Biomedical systems are consuming less and less power, and new harvesting technologies like PENGs and TENGs have the potential to supply the power needed for the safe operations of medical devices. Figure 1a shows the first demonstration of in vivo biomechanical energy harvesting using a single nanowire-based PENG. In 2009, Yang and others converted biomechanical energy from muscle movement into electricity by a zinc oxide-based PENG. This device was a single nanowire generator that consisted of a lateral zinc oxide nanowire with two ends affixed on a flexible substrate. Muscular movement drove the back and forth deformation of the whole device. By integrating multiple nanowires, the output voltage can be increased, and 4 zinc oxide nanowires in a series connection can produce an output voltage of 0.15 volts. Based on the same mechanism, Lee and others developed an implantable PENG based on single zinc oxide nanowire to harvest energy in the heartbeat of a living rat. Besides energy harvesting, some crucial results for in vivo application were also addressed in this work, such as the biocompatibility, toxicity, and encapsulation, the anchoring, and the potential for active sensing of in vivo biological motions. This figure presents schematic diagrams of the flexible PZT thin film PENG. Guerzon and others utilized a thin film PZT nanoribbon-based PENG for conformal energy harvesting and storage from motions of the diaphragm, lung, and heart. A bridge rectifier and a microbattery can be integrated with a flexible PZT mechanical harvester on a flexible substrate. The device was further packaged by biocompatible encapsulation layer to harvest energy directly from the movement of bovine heart and lung in vivo. During the cardiac contraction and relaxation, the conformal contact of the whole device with the heart without any destruction was significant importance for in vivo applications of energy harvester. The output voltage was up to 5 volts and greater by 3 orders of magnitude than previous in vivo results, when the in vivo peng was attached on the right ventricle of a bovine heart. In this work, simultaneous energy harvesting and storage were achieved by fully integration of peng, rectifiers, and microbatteries. The research indicates strong feasibility of achieving self-powered, implantable mechanical devices. This work also provides an interesting demonstration of 5 independent PZT harvesters connected serially in a multi-layered stacked flexible peng. This multi-layered flexible peng could generate an 8.1 volts of voltage and 1.2 microwatts per centimeter squared of power density, which were much higher than the output of the single-layer device. Zhang and others report a PVDF-based flexible and implantable peng, which wrapped around the ascending aorta and scavenged the energy from the pulsation. This research reveals the in vitro and in vivo studies of harvesting the energy in artery pressure with a flexible and implantable peng. In the in vitro study, the max output power, voltage, and current and of the peng were 861 nanowatts, 10.3 volts, and 400 nanoamperes respectively. The quantity of electric charging by one pulse was about 7 to 9 nanocoulombs. When implanted the peng in vivo by wrapping around the ascending aorta of a porcine, the max voltage of the implanted peng were 1.5 volts under the heart rate of 120 beats per minute and the blood pressure of 160 over 105 millimeter mercury. The instantaneous output power could reach up to 30 nanowatts with a long-lasting duration of 700 microseconds and 77.8% duty ratio. The implanted peng could charge for a 1 microfarad capacitor to 1 volt within 40 seconds. Zhang and others first demonstrated the in vivo application of TENG. In this work, an implantable triboelectric nanogenerator, or iTENG, was implanted in a living rat to harvest energy from its periodic breathing. The iTENG was fully encapsulated to protect its inner structure from physiological environment. The implantation site was near the chest, which allowed the iTENG to convert the mechanical energy from the normal inhalation and exhalation of rats into electricity and used to power a prototype pacemaker. Theoretically, the energy harvested during 5 breaths can generate a single pulse to stimulate the rat's heart. Recently, Zheng and others developed a reliable encapsulation method of TENG, which provide the TENG outstanding stability in harsh environment. Based on this technology, the same group designed a novel iTENG, which significantly improved in vivo output and reliability. A keel structure was introduced to facilitate the contact and separation process of TENG in complicated environment of a living body. Driven by the heartbeat of an adult Yorkshire porcine, the output voltage and current can reach up to 14 volts and 5 microamperes, which were improved by factors of 3.5 and 25 respectively, compared with the reported in vivo output performance of PENG and TENG. A PZT conformal pressure sensor was introduced by Dagdeverin and others. A sheet structure of PZT array was connected with the gate electrodes of a metal oxide semiconductor field effect transmitter or MOSFET to form a stretchable, lightweight, and ultra-thin devices. This device showed a fast response time of less than 0.1 microsecond, a high detection resolution with detection limit of 0.005 Pascal, high stability, and high sensitivity. After stretched at 30%, there was no impact to the performance of the sensor. This sensor was also softly laminated on the wrist, neck, and throat to monitor human blood pressure. A conformal modulus sensor or CMS within ultra-thin stretchable networks of sensors and mechanical actuators based on PZT was introduced by the same group as well. The sophisticated sensor demonstrated to measure the viscoelasticity of the epidermis in the surface regions. These conformal active sensor systems can be compactly attached to the soft tissues, organs, and various biological substrates of live creatures, which facilitate their biomedical applications. Piezoelectric strain sensors rely on PENGs that made of piezoelectric materials, which can convert mechanical energy into electricity. And they have the advantage of low power consumption, high sensitivity, and ultra-fast response. Recently, P-polymer material and zinc oxide nanowires have been used in developing piezoelectric strain sensors. A strain sensor with active matrix was reported by Sun and others, which was based on PENG-powered coplanar gate graphene transistor. Due to the external strain, the P generated piezo potential, which was coupled to the channels of graphene transistor by dielectric ion gel effectively. The piezo potential modulated the channel conductance of the graphene transistor. This strain sensor showed ultra-sensitivity and high flexibility to detect approximately 0.008% of minimum detectable strain, which were promising for human activity monitoring. Zinc oxide nanowire is semiconductive and piezoelectric material, which is also used to fabricate strain sensors. Many groups such as Tien, Kim and others, and Trong directly coupled a P and P barium titanate nanocomposite as gate dielectric layers with an organic field effect transistor or OFET. The equivalent voltage of remnant polarization inside the piezoelectric polymer was changed by the direct piezoelectric effect under external force. Meanwhile, the applied external force also led to a change of source strain readout current by modulating the intensity of the charge that accumulated between the semiconductor dielectric interface. Very recently, Ma and others proposed a self-powered and multifunctional implantable triboelectric active sensors based on implantable TENG, which can provide accurate, continuous, and real-time monitoring of multiple physiological and pathological signals. As demonstrated in large-scale animals, the device can monitor heart rates, reaching an accuracy of almost 99%. So cardiac arrhythmias, such as atrial fibrillation and ventricular premature contraction, were successfully detected in real time. Furthermore, this device also provided a novel method of monitoring respiratory rates and phases by analyzing variations of its output peaks. Blood pressure can also be independently estimated, and the velocity of blood flow calculated with the aid of a separate arterial pressure catheter. The in vivo biocompatibility of the device was examined after 2 weeks of implantation, proving suitability for practical use. As a multifunctional biomedical monitor that is exempt from needing an external power supply, the proposed triboelectric active sensor holds great potential in the future of the healthcare industry. Lately, Huang and others proposed a method to use a flexible PMN-PT thin film nanogenerator to output momentary electric energy and stimulate the heart of a living rat directly. The PMN-PT thin film pen stimulated the rat heart with electric pulses, and the electrocardiogram, or ECG, was simultaneously recorded by attached sensing electrodes. This figure showed that the artificial heartbeat generated with the assistance of PNG in an animal experiment with chest laparotomy. Before stimulating, the ECG signals showed typical PT waves and regular QRS complex with a heart rate of 6 beats per second. A few microjoule of electric power was required for triggering the action potential for artificially stimulating the living heart. When the flexible peng was bent and released periodically, corresponding electrical signals were recorded in the ECG with the cardiac bioelectricity of rat. The electric energy generated by the flexible PNG was 2.7 microjoules and capable of exciting the artificial cardiac action potential of the rat. A modified Brigman method with a stress-controlled nickel exfoliation process was used to grow and transfer thin film of PIM-NT onto a flexible substrate without any mechanical damages. This PENG stimulator can generate an output voltage of 11 volts and a current of 285 milliamperes when bent periodically on a linear stage. These results match with load impedance for the electrode of practical DBS and were adequate to stimulate nerve nuclei. A maximum output current of 0.57 milliamperes was measured when fixed and bent on a human finger. Meanwhile, the PIMNT thin film pen could light on 120 green LEDs and easily charge capacitors for the output power was about 0.7 microwatts. The demonstration of controlled body motion in a living rat was verified by stimulating a primary control motor, or M1 cortex. When the PIMNT powered the real-time DBS to activate M1 cortex with functional electric potential, the muscle contraction and the motion of the forelimb was included. Guo and others combined a highly electrically conductive RGO-PEDOT hybrid scaffold with a step-driven TENG as the electrical simulation power source to build a self-powered neural differentiation system. The electrical outputs of 250 volts and 30 microamperes were achieved by driving the TENG with human stop motion, which was sufficient to stimulate the MSC cells. The RGO-PEDOT hybrid microfiber can not only enhance the proliferation of MSCs, but also function as a medium for step-driven TENG pulse electrical stimulation signals, which can induce MSCs to differentiate into neural cells. The study realized an enhancement of MSC neural differentiation on the RGO-PEDOT hybrid microfiber under TENG-driven electrical pulse simulation. This work shows a significant potential application of a self-powered TENG electrical simulation system for the assistance of nerve regeneration. Zhang and others reported a biodegradable triboelectric nanogenerator for short-term stimulation of neural cells in vivo. The output voltage and current of BD10 were approximately 40 volts and 1 microamperes respectively. When two complementary micro-grating electrodes were powered by BD10, 1 Hz and 10 volts per millimeter DC pulse electric field or EF was generated. This DC pulsed EF oriented the growth direction of nerve cells cultured on the micrograting electrode successfully, which was crucial for neural repair.
So for the conclusion and outlook of the research article, 1. The biomedical systems and nanotechnologies are revolutionizing healthcare and medicine. Their synergy could be extremely powerful, and they could play key roles in near-term medical technologies, taking into actions the decreasing power consumption of microchips and the increasing efficiency of nanomaterial-based mechanical energy harvesters such as Peng and Tanks, which should be possible to power autonomous medical system. Autonomous medical system with self-powered and active sensing properties will be the future development direction of medical field. For easily using ex vivo and in vivo, they need to be wearable and implantable. In order to achieve this, they will need to be fully flexible to fit the size of organ, including skin closely. Thus, the device will be more discreet and comfortable for the patients and will be better adapted to their targeted tissue or organ, which will increase the sensing ability and the amount of energy harvested. Flexible electronics are currently used. Flexible microelectrons are under development, and flexible pengs and tanks are progressing. Therefore, flexible autonomous medical devices are possible, and the challenge will be integration of all parts into one small flexible device. Fully biodegradable high-performance electronics and sensors, defined as transient electronics, are another class of novel devices that under fast growing. They are fabricated with biodegradable organic materials that are used widely in medical devices. The integration of these devices could expand their functional capabilities in medicine, especially in the cases that our medical devices just need to be temporarily implanted in human body. For example, some biosensor stimulators and drug delivery systems.